So our next speaker is Dan Nocera, who is the Dreyfus Professor of Energy at MIT. Dan?
Okay, thanks. Henry Dreyfus, Professor of Energy, which is a joy because to be here at the Dreyfus event, it's quite an honor to be talking about this today. You just heard Nate talk about this is what we need to do. It's got to be cheap, efficient, and highly manufacturable. The one thing, though, you should realize about energy is 95% of the work, there's always this discover new principles of science. The bottom line is all the physics and chemistry you've done or you know about, you're not going to improve. Electrons are going to go the way they do. You're going to do electrolysis. All those principles there's no discovery there. I really don't think there's any discovery practically. Where the discovery comes is, can you do it cheaper? Can you think of new materials? Can you think of new processes? That's where the discovery comes. It comes in that top line. And so actually, I think a lot of people in the energy game have lots of wasted effort trying to find new principles when what they really want to do is have new materials and new ways to do things, like you heard Nate talk about. Nate's not changing semiconductor physics. He's making new materials to exploit semiconductor physics. So today what I'm going to tell you is the catalyst side of the story. You can see we're a tag team. And it was to try to design a catalyst to split water. And we really wanted to do it under these conditions: cheap, efficient, and highly manufacturable. And I'm going to lead you through that story today. And so I'm not even going to say what Nate said it, but the whole game of renewables is storage, I think. You get a good storage mechanism, you'll see a lot of things start getting driven. But if you have no storage, you're doomed. It's the no power after 4 statement of Nate's. So what does it? And there's the leaf. And a lot of people actually overplay sugar, because it turns out if you go and look at the Calvin cycle, there's very little energy stored here. Sugar's a good way to store hydrogen, but from an energy point of view, most of the energy storage is done up front in splitting water to oxygen and hydrogen. This, not only sugar, but cellulose and lignin, this was an engineering problem that the Calvin cycle took care of. The energy problem is taken care of up front. And so if you want to do what leaves do, you just basically can stop right here. Possibly. If you don't want to use hydrogen, then you need to do this. And I think the jury will be out ultimately whether you use hydrogen directly or not. But there's one fact: you can't avoid hydrogen if you're going to use water as your fuel source. There's just no avoiding it. So I just want to give you a little feeling, why did nature choose water as a fuel? So water, of course, isn't the fuel. It's water plus light is the fuel. And it makes hydrogen and oxygen. So you can do these calculations. In 1 liter of water, you have 13 megajoules of energy. I hate swimming. I don't know. This guy, Michael Phelps, does not impress me at all, by the way. But I went and took there's the MIT pool, 3.2 million liters of water. Now, here's the caveat. You're going to have to manage that 3.2 million per second, because I want to go into the terawatt scale Nate was talking about. Remember, we needed 15. If you manage that amount of water per second globally as your energy storage, you're up at 42.7 terawatts. So you're not dealing 1/3. You have to deal with, per second, 1/3 the volume of that pool to take care of Nate's problem. And it's all in the bonds of oxygen and hydrogen. So water and light does indeed equal oil and coal. And I want to just remind, this is a good thing. This is going to sound kind of pedantic, but what is a fuel? So there's carbon-carbon and carbon-hydrogen bonds and oxygen. I'm going to burn the fuel. Okay. Browman, It took me 14 hours to do that. It would have taken him like 36 hours to get that to happen. So that's what you're doing. You're taking high energy bonds and you're rearranging them to lower energy bonds, and then you're taking the excess energy. That's all you're doing. That's why this is so intrinsically a chemistry problem. What you're doing is you're storing energy in bonds, and it's bond rearrangements. It's what scientists and chemists do. So really what you want to do here then is take these low energy bonds, and that's what that pool calculation just showed you. You're making really high energy bonds to store fuel. And nature already knew that. That's how nature's set up to be a battery. It has membranes and it puts charges across membranes. It decided not to be a battery for a simple reason. This is an electron and this is an electron, and they have the same charge. And what your goal is to stuff them into the smallest volume you can. When they have the same charge, that's hard to do, but there's one place that you can put them in the smallest volume. That's the bond. So that's why nature chose the bond. I mean, I know it sounds simple, but I mean, the arguments I hear about energy storage are magnificent. It really is freshman chemistry. Calculate the volume of a bond, and that's the closest, that's as much as you're going to be able to stuff energy or electrons into a volume in space. I don't know if it's too bad. I think I forgot it. I had an energy density calculation. The problem with batteries is they're 3 orders of magnitude too low in energy density. You can't help it. Right? The only way you're going to increase that energy density if you go from 1 electron couples to multi-electron couples. There's been huge battery improvements. For instance, at MIT, you hear A123. Don't get confused. There's no increase in energy density. It's just a lithium iron phosphate. What the improvement in A123 is getting the energy out and in quickly. But it's not improving energy density. Right? So batteries are 3 orders of magnitude off of these bonds. And I doubt you're ever going to be able to improve that anytime soon. So here's photosynthesis again. And it is true in this Caltech-MIT collaboration, though we don't think this is the way to store energy, there's a simpler way to say what Nate was doing, and it's what you did today. You ate food. You're going to try to balance the amount of food you ate to be basically neutral because you live. So you use energy. And most of the energy getting lost, that 10% overhead, is because the plant needs to live. So you want dead stuff. Okay? So this is a dead stuff problem because I don't have to pay the energy cost for living, and dead is inorganic chemistry. So it's intrinsically an inorganic chemistry problem to boot. But let's look at, I can't help that either. Let's look at this, though, and learn from it. So what happens, and I'm going to leave out all the details of photosynthesis. What happens, though, is a photon comes in, and like Nate said, you set up a wireless current. And that's where all the engineering is in here. It's to set up that wireless current. It's to do light collection and set up the wireless current. What it then does is it slaps 2 catalysts at the end of the wireless current. So it puts a cathode over here, and it puts an anode over here. And photosynthesis had to do that. Because if you look at the solar spectrum, it can't, remember, water splitting is a 4-electron process, 4-proton process. If you look at the thermodynamic potential of water and you were to try to do it 1 photon, 2 electrons, so 1 photon comes, I move 2 electrons, you would start moving up into the UV. And you would be outside the visible spectral region. So photosynthesis was stuck. It was stuck taking 1 photon to 1 electron hole wireless current, but then at the end of the day, it has to drive a multi-electron, multi-proton reaction. So what it had to do is put in catalytic storage sites at the end network of this 1 electron charge separating species. And then the holes are stored in this anode, the oxygen evolving complex. And then the electrons are stored in photosystem 1. So that's the lesson you take from this, is in this exactly what Nate was talking about, segment catalysis from light collection and conversion. And I really think it's a losing battle to try to make one thing to do everything. And it turns out, of course, you need both the oxygen and hydrogen to get maximum energy storage out of water. Water is renewable. The biggest problem, we have we have platinum that works great for hydrogen. It's rare. Okay. We have other catalysts to do hydrogen. The thing that's been difficult is the oxygen, getting this other side out. Platinum does not work well with oxygen. It's just not compatible chemically with oxygen. And so the real issue is, for us, this is the problem we attacked, is how do we do this efficiently under simple, cheap, highly manufacturable conditions? And in December, we decided to backtrack because we weren't getting very far. Everything we did, we had ruthenium, this ruthenium oxide catalyst. There were molecular compounds. We would get 100 turnovers, 1,000 turnovers. We didn't even publish those papers. The catalyst would die. So what we did, I'm going to just lead you through the last 8 months in the group, and I'll show you the student who did this or started it. But we just sort of had a self-help session. As a lot of you know, I need those sessions frequently. And so we decided to have a little sort of therapy session in December called group meeting. And we just said, let's go back to photosynthesis and let's start evaluating our biases. And we realized we had tremendous biases. So here's the first one. Photosynthesis. There's Jim Barber's crystal structure, an amazing, I think, one of the most amazing contributions in the last few decades to science, just because I love photosynthesis. He got the crystal structure. The Berlin group has, and then the Berkeley group in XAF. So those three groups have put in front of us now what the leaf looks like and what the machinery looks like. So we have the Kodak moment of photosynthesis. And that looks really complicated, and the complexity is overwhelming. But then we started looking at this and said, in terms of making oxygen, getting that oxygen side, this is a little piece of rock. It's manganese, oxygen, calcium, oxygen, manganese. That's it. So you look at this incredible complexity of photosynthesis, but you realize the thing that's making oxygen is a piece of rock, just simple metals with oxides in a cube. The next thing you realize, and Nate alluded to this, and this is the one that really messed us up, and we realized how much of our life was getting sidetracked by this problem. If you're in this business, Eric is in the business, he was talking about catalysis. You make a catalyst, what's the first question they always ask? How stable is it? How stable is it? How stable is it? And so this is what inorganic chemists do. We finally can induce stability. We will make ligands and put them around metals, and I don't care what you do to that metal. We'll try to make that metal be stable under whatever oxidation state you want. And we realize that's a mistake. And the reason is, as you come to this system, and this is what Nate was talking about in terms of overhead, this is the D1 protein. This cluster sits in that D1 protein. And around every 30 minutes, 40 minutes, it's so oxidizing in there that this system starts off and will take sulfate. From sulfate, it makes cysteine and then sets up a biosynthetic pathway. Every 30 minutes, it remakes the D1 protein and then reinserts the manganese cluster. So this thing is massively unstable. But you don't care because it seems to work. So here was the thing we had to release ourselves from for this problem. When we started talking about stability, and I know, again, this sounds simple, but you can't believe. I mean, it's just, I guess, our biases was messing us up. It's functionally stable. When we say stable in this game, what we're really saying is functionally stable. A lot of times people misinterpret that as structurally stable. This is massively unstable structurally, but it's functionally stable. And then finally, O2 is made from neutral water, low over potential. You need proton carriers. So these were the things we decided to retarget in the design. And now I'll just quickly go through a catalyst design. There were two other pieces of information we had. And one is this is photosynthesis. Light comes in, and you're making oxygen and hydrogen. Hydrogen goes into sugar. You eat the green leaf. When you eat the green leaf, it goes into your body. In your mitochondria, you have the fuel cell, cytochrome C oxidase. It literally undoes what photosynthesis does. It takes O2 plus 4 protons and 4 electrons and goes to water. Whether you realize it or not, I mean, just think about it. When you eat green leafy vegetables, what do you chew on? You're not chewing on the plant, you're chewing on the sun. Because those photons literally got stored in those bonds, which is released from cytochrome C oxidase. So when you chew leafy vegetables, you're just crunching the sun. You're eating it. And that's because of this thing, cytochrome C oxidase. Now, why was that important to us? This was my old friend. He actually taught me everything about photosynthesis when I was a young guy. Jerry was one of the few people who could have done this. By the way, he's died because of lung cancer. I have like 1,000 pictures of Jerry, and not one doesn't have a cigarette in his mouth. I just tried to find one without a cigarette. I couldn't. But Jerry is the only guy who could have said something like this because he studied this, photosystem 2. He was the guy who identified the tyrosine radical in photosystem 2, the famous tyrosine radical for the experts. And what Jerry had done is said, and I've dressed this up with the new structure. He used the old structure. The new structure wasn't known at the time. But Jerry even said, not only is it sort of the thermodynamic reverse, but look at this chemically. To make O2, this is one of the prevailing thoughts of making O2, that a hydroxide, this deprotonates, hydroxide attacks oxo, you make an OO bond. It's not very different than Eric's chemistry. A nucleophile is hitting an electrophilic oxygen. When Eric does his chemistry, it's a nucleophilic olefin. So a lot of the work, just again to show you the complexity of these problems, a lot of our design has been following Eric's manganese oxo work. Because it's the same thing, I'm just going to use a different nucleophile, hydroxide. Jerry was also studying cytochrome C oxidase by Raman spectroscopy, and these are the postulated intermediates of cytochrome C oxidase. It's exactly the opposite. I mean, that I still find, this is when nature is beating you over the head. Not only is it thermodynamically the same way, it's almost down to the microscopic atoms of how you make and break bonds it's undoing it. And you look a lot different than a leaf. But chemically, you aren't.
Smarter.
What? I don't know. Leaves are pretty smart. And then what we did, to start studying this, a few years ago, we started studying the O2 reduction process. And I don't want to go through this whole thing. A lot of you know we spent a lot of our life studying this idea of proton-coupled EDT. How do you couple electrons to protons to drive multi-electron reactions? This was incredibly important to that understanding. If you look at this, oxygen goes in, and I'm picking up one electron. Cobalt 2,3 goes to 3,3, so I go to superoxide. What we figured out for the O2 reduction problem in these cycles, this is the key intermediate. If this is basic enough, it takes up a proton, and then it drives a 2-electron reaction. So that's the PCET. You couple a proton to drive the multi-electron reaction. If we made these systems where this wasn't basic enough, it wouldn't pick up a proton. It would simply pick up an electron and then release peroxide, which you don't want to do in a fuel cell. In a fuel cell, you want to go O2 to water. So there's lots of lessons here. First, cobalt's a good metal for handling oxygen. Part of the reason is it doesn't make too strong a metal-oxo bond, so you can get it on and off. Secondly, you want to do this is sort of the Jerry intermediate, the oxo-hydroxy. It's all here, and you got a couple proton transfer to get there. So we spent 3 years learning about how to run the downhill reaction. And then we were presented with a few problems to go the other way. And so here's the first one. And now you'll understand why we were so bothered by the stability issue. There is not one mechanism. So if you come back here, every single time you're going from cobalt 2 to cobalt 4. There is no way to avoid these oxidation states with cobalt. You're always going to have, no matter what mechanism, if I do this is kind of a radical coupling mechanism, or if I do the sort of Eric Jacobson nucleophilic attack on an oxo, I'm at cobalt 4, I'm on cobalt 3. So now we'll go to freshman chemistry. The rest of this is a freshman chemistry lecture. You take cobalt 4 or 3. It's a D6 cobalt. Harry, my old boss, got his PhD with Basolo telling everybody when you're D6, you are substitutionally inert. It's a rock. When you go to D7, you go high spin and the ligands begin exchanging. That's cobalt 2. So I have a real problem on my hands. If I'm going to cobalt 2, this thing is going to lose ligands. It's unstable structurally. If it's here, it's stable. Now, I told you inorganic chemists can almost do anything, and we can. So what do you do? How do you attack this problem usually? Well, it's unstable. I will enforce a ligand geometry so that it can never come off. I'll put a chelating. I'll put it in a cage. So that's what inorganic chemists do. What's the problem there? It's the ligand field argument. If that ligand structure is stable for cobalt 3, I'm telling you it has to be unstable for cobalt 2. If I force the ligand to stay on cobalt, I'm doomed, because I'm going to have the overpotential of forcing the electron into this electronically unfavorable situation. So what we started to realize is we're always building in overpotential. So we don't want to do that. We want this to be unstable. And then, so I'm just connecting the dots of how we work through this problem. So we have cobalt 2 we know is going to be unstable. Cobalt 3 we know is really stable. There's 9 orders of magnitude difference in this stability issue. So that is a good thing. That gave us an inkling of how to control this cobalt. Cobalt 2 becomes unstable, but if I bring it back to cobalt 3, it will go back together again. And you got to figure, so what we started thinking is we could establish a healing mechanism, sort of a repair mechanism, a simpler one than the leaf, that if we do make cobalt 2 and it does escape, we can bring it back to cobalt 3. The next thing is what do you do it with? And we literally went to the freshman chemistry books. This is 1 KSP we could get. Now this isn't cobalt, that's calcium, but that's 2 plus 2 minus. Cobalt is 2 plus 2 minus. So that's kind of our electrostatic, bringing a 2 plus 2 minus together involving phosphate. And then what we knew is if we put these ligand field arguments in, D7 is going to be high spin, unstable. So it's going to have a smaller KSP, or bigger KSP. This will have a smaller KSP because it's cobalt 3. So phosphate looked good to us to be this carrier, this transporter of cobalt if it were to become unstable. And then this guy, Steve Reese, we have been studying proton-coupled electron transfer for years. And in 2007, we worked out lots of details. Some of you know I worked with Joanne Stubby on ribonucleotide reductase. It's a big enzyme in your body that does radical enzymology based on tyrosine. And the way we figured out how to activate tyrosine in ribonucleotide reductase is we can put on end caps to the peptides, drive electron transfer this way, but we need to dump the proton. And what this study showed is that HPO42- is perfect for this proton-coupled ET, absorbing the proton. Now, you're in water. You can't absorb the proton with H2O because you make a strong acid, H3O+. So even though there's a ton of water around, it's a lousy base for protons. You can go to OH- if you want to stay under simple pH 7 conditions, but the problem is there's not enough of it. So the phosphate ends up being the thing you couple electron transfer to. So phosphate had 2 purposes for us. One is it could give us a repair mechanism And then secondly, it could be the proton carrier and the activation of this cobalt and the oxygen-oxygen bond breaking. So here's Matt Cannon. He's an organic chemist from Harvard, worked for David Liu, came to my group to learn some inorganic chemistry. And I'm just showing you because this is such a terrible cell design. Over here is a piece of glass. We use ITO. You can use any conducting surface. We used ITO because it has a big overpotential for making O2. We didn't want to get confused by the electrode participating. So it's pure glass. You can see through it. Over here's platinum. Here's a frit. Here, and we just put water, and then we put the phosphate in there, HPO42 minus. This is how simple it is. Turn on the potential. You go up. In our case, this is 1.3 volts versus NHE. Remember, making water to O2 is around 0.9, so we're a 4/10 past where we should be. This is to prepare the electrode. And you'll start seeing current rise. So the current's going up. So the electrode is absorbing current. And if you look at different periods, you start seeing this cobalt phosphate film forming. Absolutely amorphous. Okay. You can grow it to any thickness you want, pull it out, and then put it in pure phosphate, and you can control the film thickness. If you just leave it in, it will go to around 2 to 3 microns. But you can grow this to around 50 nanometers. It will go on any surface, over any area you have, over any geometry, which is good if you remember Nate's talk about all those little trees, because we're going to have to get this catalyst on there. It's an amorphous material. And this thing, when you're looking at it as the film's forming, you're seeing lots of oxygen come off. And what I'm showing you here is that all the oxygen's coming from water. If you use isotopically labeled water, here are the predicted isotopic statistical amounts of 16, 16, 16, 18, 18, 18, and we're dead on. So every bit of oxygen's coming from water. Phosphate is not decomposing. We've done the P31. There's nothing else. Cobalt can't make oxygen. It can't transform into oxygen. So everything's coming out of water. If we extrapolate, the overpotential is around 0.3 volts, 0.28 volts. There's a pH dependence that you can basically turn into an overpotential. And the reason why that pH dependence is interesting is, and we're pretty sure of this now, we're doing in situ XF studies. We can see the cobalt-3 and cobalt-4. And it's just like that cycle I showed you with the porphyrin. It looks like it's a cobalt-3 hydroxide. You oxidize. This is sitting on an electrode. You bring it up to cobalt-4 in a proton-coupled electron transfer step, and you make that cobalt oxide. And that's where we see O2 production. So we're doing a lot of in situ XFs. We even have almost the structure of the active site. It's going to be a big surprise to people. It is a molecular entity, and it doesn't look a lot different than the oxygen evolving complex of photosystem 2. So it's an oxocube. You can use methyl phosphates, so you can use other buffers. This is methyl phosphate. What's cool about this is you can put it into chloride. Now, usually you make chlorine or hypochlorite in salt water. This is up to 0.5 molar. This is 0.5 molar sodium chloride, and you can see that we're beating out at this pH and this overpotential. We're beating out chlorine production. So you can use salt water and you can make O2. And then these are our latest results. Remember, I talked about this repair mechanism. We can make 32 isotopically labeled phosphate. And you can watch, if you have this under potential, you see phosphate exchanging. So we put hot phosphate, we make the hot phosphate electrode, and then just put it in a cold phosphate solution. You start seeing the hot phosphate show up. If you turn the potential off, remember, you're cycling. If I turn the potential off, then it has more time to go to cobalt-2. It's substitutionally labeled. You get more phosphate in solution. So when you're under cycling, you're not making cobalt-2, or you're reoxidizing it more quickly so the phosphate can't get out. Danny has also done hot cobalt. So here's 57 cobalt. If you turn the potential off, you just make the hot cobalt and put it in a pure phosphate solution, you'll see cobalt showing up in solution. If you then turn the potential on, you see the cobalt getting sucked up. Turn the potential off, it starts going off. Turn the potential on, it goes right back on. So that is unequivocal evidence of this exchange mechanism. I want to enforce, it's not a lot. This is only 2%. So the thing's pretty stable. But even the little parts, because you are making cobalt-2, it is substitutionally labile. We have this repair mechanism. So these films are just stable. You can let them go for days. They just don't change in phosphate. So this is, I'm just going to give you the quick mechanism, is you can take cobalt-2 to 3. Once it's to 3, phosphate puts it on the electrode. You get to cobalt-4 oxide. We still need to nail this down, but all the XFs, beautiful edge for cobalt-4 oxide. We've been doing this at Stanford in the linear accelerator. We can do it in situ while the electrode's running. We come in the back on a Mylar electrode. That thing then makes O2. You come to cobalt-2. You reoxidize that up. If some of it falls off in solution, you pick it up with phosphate and you repair it. So that's how the cycle's working. I don't look at it as homogeneous or heterogeneous. It's both. Okay. It's all occurring at a molecular center. We wouldn't be able to beat out chloride if it wasn't. If you had a density of states in a solid state material, you would be oxidizing chloride to chlorine. The bottom line is the outer sphere electron transfer of chloride to chlorine just can't beat out the inner sphere reaction of oxygen. That's very molecular thinking. And because it's a molecular system, we have the ability to control it. Here, all you have to do, I showed you a milliamp per centimeter squared, just increasing the surface area. And this is in methylphosphonate. We just bring up the phosphate buffer. And now you get up to 10. This is 10 milliamps per centimeter squared. Here's the O2 being made. This is real time. Then over here, we're making hydrogen. Now, we're applying a potential to this. I'll get to that in a minute. Here's the electrode, a close-up of the electrode. The O2 is pouring off of this. We think it's running per cobalt right now at around 200 to 1,000 turnovers per cobalt per second. So this thing is really churning it out. Where we have a terrible cell design. Well, let's look at this. This is what manganese is. It's self-assembled from manganese. Actually, upon oxidation, the core self-assembles. This is self-assembled from cobalt. Cobalt's pretty cheap, not like iron, but if you remember Nate's chart, it's in a good zone. You have phosphate to do the equilibrium in place of the D1 protein, and everything that's happening in terms of O2 generation here, we're able to do here, and it's better because it's cheap. This is expensive to do. It's highly manufacturable, and it works in the presence of impurity ions. This is what we're doing now, though. Remember, an electrical current's coming out of the wall. So now you see where Nate and I are like this, because now, again, you separate catalyst function from charge collection. And this stuff you can just lay down on any surface. So I think we're ready to go for Nate right now. And so you drive this, and then you do this reaction. And that will have all the things like Nate said of an artificial leaf. And I just want to just tell you something to recalibrate. If I just take this catalyst with the ohmic drop, because we have ohmic drop, I got to move protons from one electrode to the other side. All right? And I take that ohmic drop, I take the overpotential on cobalt, and then I had platinum on the other side. In this calculation, we've been able to use a nickel alloy, and we're 0.2 of a volt over for hydrogen production to get rid of the platinum. Taking all of just that function of the catalyst for 30 meters squared PV, run-of-the-mill PV, I think this was for 12%, you get 6 million amps. The average house needs 20 kilowatt hours a day. That's only 5.5 liters. This is you're not dealing with a lot of water. You can store the amount of storage that an average house in America uses. That means this thing was running at 10 milliamps By the way, if we go up to, right now we have stuff from Corning, 250 meters squared. Okay, so this is a cheap catalyst. You can just put as big a surface area as you want in the smallest area. In 2.5 hours, you generate enough hydrogen, you do enough hydrogen storage. For that part, I mean, in the full system, you got to send it through a fuel cell, so multiply by another 2 hours. The point of this is you're already in the ballpark to start thinking about doing storage at a local level. So this thing, I don't think is as far off as scientists believe, because you can just see with the science that Nate and I are talking about, we aren't that far off of taking care of this vision. I really believe it. We went to the damn moon. Are you telling me we can't do this when we're almost in the ballpark? And this is the deal. We've done it before. So 70s mainframe, then PCs, and look what happened to mainframes. Right? Here's the mainframe of energy, personalized energy. Look what happens to the mainframe. So I am out to destroy the grid. I mean, I get people, I really am. I will destroy the grid. I'm committed to destroying the grid. And it's an easier problem because in this system, you have to re-network. In this system, the end user, you're done. Right? Maybe in a smart community, you might have a little networking. But it's a much easier problem in terms of a systems problem. So let me tell you where we are. This is the last slide. In this instance, just using this as an electrolyzer. So you can make a cheap electrolyzer now. We're making cheap electrolyzers out of plastic using this stuff in water. That's something we're doing in our lab right now. This is cheap. But in the full system, you have also the PV, what Nate talked about, the fuel storage. If it's hydrogen, you got to do compression. And then you need the fuel cell. All right? If you use batteries, you can dump this, but I can already tell you, I'm doing a big energy study. Batteries are never going to be economically competitive. They have no hope because of this 3 order of magnitude energy density problem. So drive your cars on them, but you're not going to be storing this amount of energy with them. So here's the 4 components. Let me just tell you what's happened since the discovery. If anything, it's become like a lightning rod for this personalized energy thing. So you've got to start partnering to do this. I'll tell you who the PV company is. It is Wacker. They're ready to go with large-scale manufacturing to try to figure out exactly what Nate says, to get costs down, to try to make, and then put this catalyst on it. This part, I wasn't so confident about this. When I was on, at first I said 10 years. Then I was on CNN and I said somebody said, how come scientists always say 10 years? So then when I went on CNBC, I said 8.1254 years. And now I'm down to 5 years. I really believe it. And it's not because of this discovery. This part, fuel storage and fuel cell, Air Liquide's vice president, she got on a plane the day the paper came out, was in my office that morning. They have amazing technologies that have been sitting on their shelf. So this whole thing right now is just a new let's now do design to cost and not over-design for this personalized energy need, especially in the developing world. So this is just using the system as it is now. The people I decided to partner with were not energy people. It's always yes, but, yes, but, yes, but. We have a grid. You're crazy. You know the PC guys? They've already done it. So you know the names of the people who are signing up for this. So it's the Sun Microsystem guys. It's the Ethernet guys. It's the Mac guy. Okay? They really want to do this now. But what Nate was saying is, in all of these things, why doesn't the third world or developing world have a grid? Because they don't have money. So you can't they can't buy this either, right? So this whole thing is, what science are you going to do to keep driving costs down? And now I don't need to talk to you about this. This is exactly what Nate said. But this is now easy to interface. We have a nickel alloy that's kind of okay. It's working in water. Now, why is that important? Look what you do there. That's a big cost saving. So I don't know how a lot of you feel. But once you start working through these numbers, this idea of personalized energy is not far off. And now I will tell you, there's a really committed team of people, some really famous business people actually on the board of Caltech, who are they've come out of retirement. We talked them out of retirement. And they are supercharged to see this go. And I don't think it has to be far off. And so now we have to do the hardcore reality of what we really need to get back to your question, Mark, and then do design to cost. It turns out very few people have done those calculations. They kind of throw numbers around, but really haven't, especially in the developing world. I will tell you here, we have all of India taken care of for distribution. So the Tata brothers are ready to go. We have North Africa ready to go. China's a much more complicated beast. We're working on that. But I'm going to give myself 5 years. If I don't do it, you can make all the fun you want out of it. Okay, with that, thank you for your attention. Yep. Yep. Well, so that was kind of in that number that I was using at that 20 milliamp. That's sort of your run-of-the-mill 12%. I think was 280 watts per meter squared. So that's what that number is right there. 280. Average. That's average. That's what you want with storage.
Yeah, I mean, your whole point here is storage carries you through.
It's the storage. I mean, I was at the Clinton Global Initiative, and I was there with T. Boone. And we all had to just give one word. And I forgot what T. Boone said. But, money. But it's just storage. That's the only word. So it's just storage right now, I think. I'm simplifying the problem. Look, PV has real costs. So there's got to still be an amazing amount of science done. But I really believe we're capable, and I think we're missing the point by not selling this to the public. I will tell you, after this came out, I literally have over 10 to 15,000 emails from people who said, please use my house. It's an incredibly empowering concept. This energy thing people are afraid of. It's over there. It's from a foreign country. All of a sudden, they're saying, wait, I could live like this? Why hasn't anybody at least had this discussion with us? I will tell you, the Senate got overwhelmed with messages, so now the Senate wants to see me just to find out what the hell I'm talking about. But I don't see why, as a community, we should not be selling this message. I think it's doable. Of course, it's going to be with huge commitment. You're going to empower the scientific community, right? So it's not going to happen the way it's getting funded now. But if we went to the moon, you're telling me I can't do this? And I will tell you, the number of technologies that have come through my office from these big companies, it is stunning.